Dear students, let us start crystal field theory, in which we are going to discuss distribution of electrons in strong and weak ligand field. Up till we have discussed distribution of d electrons d1, d2, d3, d4 and d5 in strong and weak ligand field. Today, we are also going to discuss CFSE, that is crystal field stabilization energy, as well as evidences for crystal field stabilization energy. Let us see. Filling of d6 electrons in strong and weak field. d6, this is free metal ion d orbitals. Here there are 6 electrons. This position of d electron remains same in hypothetical symmetrical field. That means when ligand approaches to metal ion, the energy of d orbital is increases. So here there is increase in energy of d orbital. The position of 6 electron remains as it. Now there are two types of splitting: weak ligand field splitting as well as strong ligand field splitting. First we discuss how the electrons are filled in weak ligand field splitting. So see here, these are Eg orbitals, their energy is increased, while these are T2g orbitals, their energy is decreased. This is the difference between Eg and T2g, which is given by 10 dq. The 10 dq value for weak field splitting is smaller, and hence the filling of 6 electron takes place in this way. So first electron goes into T2g orbital, second goes into T2g orbital, third electron goes into T2g orbital. Now as this 10 dq value is smaller, fourth electron easily enters into first Eg orbital. Then this is fifth electron, which also enters into second Eg orbital. And now see, sixth electron is paired up with first electron, which is present in T2g orbital. So in this way, in weak field, the electronic configuration is T2g4 Eg2, which contains 4 unpaired electrons, and therefore these complexes are called as high spin complexes, which shows spin is equal to 2, S is equal to 2. Let us see next field, that is strong field. In strong field, what happens? First electron enters into T2g orbital, second enters into T2g orbital, third enters into T2g orbital, but as the value of 10 dq is larger, this value is higher, therefore fourth electron is not enters into Eg orbital, but it pair ups with the first electron in T2g orbital. Fifth electron also pair up with second electron. Sixth electron also pair up with third electron. So all 6 electrons are filled in T2g orbitals. So in strong field, the electronic configuration is T2g6, in which there is no unpaired electron. Got it? There is no unpaired electron, and hence the value of spin is equal to G. This is the difference in weak ligand field and strong ligand field. In weak ligand field, there are 4 unpaired electrons, while in case of strong ligand field, there is no unpaired electron. Then see D7. So this is free metal ion. D orbital contains 7 electrons. In hypothetical symmetrical field, the position of electron remains same in d orbitals. And now see, in weak field what happened? This is the first, second electron, third electron enters into T2g orbital. Again, as 10 dq value is smaller, the fourth electron enters into Eg orbital. Fifth electron also enters into Eg orbital. And this is the sixth electron pair up in T2g orbital. Also 7th electron pair up into second electron in T2g orbital. Hence in T2g orbital there are 5 electrons, and in Eg orbital there are 2 electrons. So electronic configuration in weak field is T2G5 and Eg2, which contains 3 unpaired electrons and the value of spin is 3 by. Okay? So it contains 3 unpaired electrons. Now you see in strong field what happened? In T2G orbital there are now 6 electrons. First electron, second electron, third electron in T2G orbital, fourth electron not enters into EG orbital, it pair up with T2G orbital in first orbital, fifth electron pair up in second electron in second orbital, again sixth electron pair up with this third electron in third T2G orbital. Of course, as these T2G orbitals are completely filled, seventh electron enters into EG orbital. Hence, electronic configuration is in T2G orbital there are 6 electrons, in EG orbital there are 1 electron, and hence this contains 1 unpaired electron. The value of spin is half. This is the difference in electronic configuration. There are difference in unpaired electron. In weak field there are 3 unpaired electron. In strong field there is only 1 unpaired electron. This is about filling of D7 electrons. Then see D8. For D8 electrons, the field splitting of weak and strong is same. So filling of D8 electrons in strong and weak field is like this. This is free metal ion orbitals. Here this d orbital contains 8 electrons. In hypothetical symmetrical field, this electron remains as it is. And now see, in weak field as well as in strong field, this is Eg orbital, these are T2G orbitals. Filling of electron remains same in both fields. T2G orbitals are now completely filled. They contain 6 electron and 7th electron enters into first EG orbital and 8th electron enters into second EG orbital. So in both field, in weak field and strong field, the electronic configuration is T2G6 Eg2, which contains 2 unpaired electron and the value of spin is 1. Okay, so for D8 configuration, for D8 electron, the filling of electrons is the same in both field, in weak field as well as in strong field. Now see, for D9 electron, again here also the filling of electrons in strong field and weak field is same. How it is? Let us see. Free metal ion d orbital, okay, contains 9 electron. When they are in contact with ligand, energy is increases. Again, the position of electron, 9 electron remains same. This is called as hypothetical symmetrical field. And now see, T2G orbitals in both field, weak field and strong field, contain 6 electron, while EG orbital, first EG orbital contains 2 electron and second EG orbital contains 9th electron, that is third electron. So electronic configuration in both field is T2G6 Eg3, which contain only one unpaired electron, this one. Okay, so one unpaired electron is present and therefore the value of spin is half. Now see next one, filling of 10 electrons, D10 electrons in strong field as well as in weak field. So this is free ion metal d orbitals, contains 10 electron. When ligand approaches to metal ion, energy of d orbital increases, but the situation of d electron remains same. All d orbital contains 10 electron. Now see again, T2G orbitals are completely filled. 3 T2G orbital contains 6 electrons and 4 electrons now enters into EG orbital, 2 in first EG orbital, 2 in second EG orbital. All orbitals are completely filled. That means this decrease in energy is balanced by increase in energy. Got it? So electronic configuration for D10 system is T2G6 Eg4. All orbitals are completely filled. There is no unpaired electron, and therefore these complexes have spin value 0. S is equal to 0. Let us turn to next point, which is called as crystal field stabilization energy, CFSE. In previous lecture, we have discussed that when ligands are approaches to metal ion, what happens? The energy of Eg orbital is increases, the energy of T2G orbital is decreases, and then in these orbitals, in T2G and Eg orbitals, we have to fill the electrons. For this purpose, some energy is required. That energy is called as CFSE, crystal field stabilization energy. Let us see definition. The total decrease in energy caused by splitting of the d orbitals and their occupancy by electron is called as crystal field stabilization energy, CFSE. If electrons are paired, then we have to add pairing energy. So in case there is pairing energy, so P is involved, it is added to the crystal field stabilization energy. Let us see equation. How CFSE for octahedral complexes is calculated. So this is the equation. Number of electrons in T2G orbital into its energy minus 4dq plus number of electrons in Eg orbital into its energy plus c. So the CFSE for D1, D2, D3, D8, D9, D10 system in strong and weak field in octahedral complexes are same. In previous slide, we have discussed the filling of these D1, D2, D3, D8, D9, D10 system in both field is same. Got it? There is no difference in electronic configuration when electrons are filled in strong field and in weak field octahedral complexes. Again I repeat, so CFSE in both field for D1, D2, D3, D8, D9 and D10 system is same. How it is same? Let us see. So this is the again formula. Number of electrons in T2G orbitals into minus 4dq plus number of electrons in Eg orbitals into plus 6dq. So for D1, 1, there is only one electron. That electron enters into T2G orbital. So 1 into its energy minus 4dq. Therefore, CFSE for D1 system is minus 4d. For D2 system, 2 electrons enter into T2G orbital into its energy minus 4dq. So 2 into minus 4dq, it becomes minus 8dq. So this is the CFSE for D2 system in both weak and strong field complexes. Similarly, this is D3. 3 electron enters into T2G orbital. Its energy is minus 4dq. Therefore, 3 into minus 4dq, it becomes minus 12dq. Then D8 system, 6 electron now present in T2G orbital. It is multiplied by minus 4dq, its energy, plus 2 electrons are present in Eg orbital into its energy plus 6dq, and 3 electrons are paired which are present in T2G orbital. So pairing energy is added. Hence, so 6 into minus 4, it becomes minus 24dq plus 12dq, it becomes minus 12dq plus 3p. This is the CFSE in both field, strong field and weak field for D8 system. For D9 system, the electronic configuration is T2G6 and Eg3. So 6 electrons are entered in T2G orbital, therefore 6 into minus 4dq, 3 electrons in Eg orbital, therefore 3 into plus 6dq, plus 4 electrons are paired, therefore that pairing energy is added, hence it is minus 6dq plus followed. Similarly, for D10 system, electronic configuration is T2G6 and 4 Eg4, that means 6 electrons are in T2g orbital, therefore 6 into minus 4 dq plus 4 into plus 6 dq, it becomes 0. Minus 24 dq plus 24 dq is equal to 0. Followed? So for D1, D2, D3, D8, D9, D10 in strong field and weak field, we have calculated the CFSE values. Now let us see for system D4, D5, D6, D7 in strong and weak field octahedral complexes, CFSE values are different. How these are different? Let us see. First we discuss in strong field complex. Again I repeat, the formula, the equation remains same. Let us see. For D4 system in strong field, all electron enters into T2g orbital. So T2g contain 4 electron and therefore 4 into its energy minus 4 dq. 1 electron is paired in T2g orbital, therefore energy is minus 16 dq plus. Then D5, all electrons enter into T2g orbital, therefore electronic configuration is T2g5, hence energy is 5 into minus 4 dq plus 2 electrons are paired, therefore 2p, hence CFSE is minus 20 dq plus 2p. 5 into minus 4, 20 dq plus 2. Then D6 system, all electrons are paired in T2g orbital. All electrons are present in T2g orbital. Therefore 6 into its energy minus 4 dq, that is minus 24 dq plus 3p, and hence minus 24 dq plus 3p. This is the energy for D6 in strong field complex. Then next one for D7 system, all T2g orbitals are completely filled. 6 electrons are present in T2g orbital. 1 electron is promoted into EG orbital. Hence, CFSE is 6 into minus 4 dq plus 1 into plus 6 dq, that is the energy of EG orbital. Therefore, minus 24 dq plus 6 dq, it becomes minus 18 dq. 3 electrons are paired. Therefore, this is plus 3p. So, this is the CFSE calculation for D4, D5, D6, D7 system in strong field complex. Now see, calculation of CFSE in weak field complexes, formula remains same. Number of electrons in T2g orbital into minus 4 dq plus number of electrons in EG orbital into plus 6. So see, for D4 system, now electronic configuration is changed. T2g contains 3 electrons and EG orbital contains 1 electron because the value of 10 dq is small. 4th electron is promoted into EG orbital. So 3 electrons into minus 4 dq, this is for T2g system, plus 1 into plus 6 dq, this is for EG orbital. Hence the calculation shows that the CFSE is minus 6 dq. Minus 12 dq plus 6 dq, it becomes minus 6. Then for D5 system, 3 electrons are present in T2g orbital, 2 electron enters into EG orbital because 10 dq value is small. Hence 3 into energy of T2g orbital minus 4 dq plus 2 electrons in EG orbital into plus 6 dq. So plus 12 dq minus 12 dq, it becomes 0. System becomes stable. For D6 system, T2g contains 4 electron, EG orbital contains 2 electron, hence 4 into minus 4 dq, that is minus 16 dq, 2 into plus 6 dq, electrons in EG orbital. So 2 into plus 6 dq, it is become plus 12 dq. Hence the subtraction shows that this is minus 4. Similarly for D7 system, 5 electrons are enter into T2g orbital while 2 electrons are enter into EG orbital. This is the electronic configuration. So 5 into minus 4 dq plus 2 electrons in EG orbital, its energy is plus 6 dq plus 2 electrons are paired 2p. Therefore minus 20 dq plus 12 dq, it becomes minus 8 dq plus 2p. This is about the calculation of CFSE for D4, D5, D6, D7 system in weak field complex. Now see next point, evidence for crystal field stabilization energy. The CFSE plays an important role in thermodynamic properties of transition metal compounds like lattice energy or heat of hydration. Due to CFSE, many complexes are stabilized. Complexes with D0, D5 and D10 ions have no CFSE. Remember well, D0, D5 and D10. These have no CFSE. They show regular gradation in properties. In which properties? Like lattice energy and heat of hydration. While other complexes, that means D1, D2, D3, D4, D6, D7, D8, D9, that means other than D0, D5 and D10 shows irregularities in these properties, lattice energy and heat of hydration. Let us see with the help of graph. On this axis there is lattice energy and on this axis there are these systems D0 to D10. See this graph. This is the point for D0, this is the point for D5 and this is the point for D10, that means zinc. Here we see that for these systems D0, D5 and D10 there is lattice energy increases regularly. But see this system D1, D2, D3, D4, this lattice energy value not regularly increase, that is irregular gradation. Similarly for these D6, D7, D8 and D9, irregularly these values, lattice energy values are increases. But when we subtract lattice energy from this point, what happened? These points fall on this straight line. Follow? This gives the evidence for CFSE. This is the graph for heat of hydration for divalent ions of metal from calcium to zinc. See, this is 0 for calcium, that means D0. This is manganese D5 and this is the point for heat of hydration for zinc D10. So regular increase in heat of hydration is observed for D0, D5 and D10. And again we observe that for this system D1, D2, D3, D4, D6, D7, D8, D9, there is no irregular trend in heat of hydration. Okay, and when we subtract heat of hydration from this point, what happened? This point fall on this straight line. In this way, the complexes become stable, and this gives the evidences for heat CFSE value. This is the equation. How heat of hydration is released. Metal ions in gaseous form, when reacted with water molecules, there is formation of this aqueous complex, and at that time the energy is liberated, that is called as heat of hydration. In this way, this is about the evidence for crystal field stabilization. This from above graph we observe that the straight line passes through D0, D5, D10 system which have no CFSE, while points for other ions lie above this line. On subtracting CFSE from each lattice energy or heat of hydration, the points fall on straight line. This is already discussed by us when we have discussed about graphs. So friends, today we stop here, and in next lecture we discuss the next point of the same chapter, crystal field theory. Thank you.